Okay. Um, I think uh, interesting thing about the seismic isolation is that all of the interesting stuff or this it would all be very easy if it worked ideally. And as Peter points out, there's this very important point of the internal mechanical resonances. So um, the idea that often people have of let's just make the first stage have a resonant frequency of 1 millihertz. It just doesn't work because of these kinds of problems. And there's many other dirty things that come in. And so I think it's important to go through and list something like why don't these various ideas work? What are the problems with these? So I will describe a little bit more about the sources and nature of seismic noise, and then belabor the point about seismic sensors for most of this thing. And then because we are talking about feedback a little bit later on, I don't want to get into the details of this feedback system, but just draw for you how it works without calculating the details of these feedback systems. But then we'll reintroduce it after the introductory lectures about feedback systems. So this is the um, correspondence to what Peter showed of the power law. So this, if you look, there's a very faint line on here, which is this thing, 10 to the minus 8 over f squared. So this is what we often assume for the background seismic noise in a quiet site. So there's a few different ones I'm drawing here. These red and green ones are the U.S. LIGO sites. These are noisier than quiet sites in India. This light blue one here is the pretty high seismic level at the site, Virgo site, which is maybe one of the reasons they needed to have such a good isolator. They're really an order of magnitude or more worse than the quiet LIGO site. And the quiet LIGO site is not even so quiet. It's quiet around 1 hertz, but then you look at some of these other places. If you really start looking around, and on the Earth, you can do much better in this band from 1 to 10 hertz. This first one, yellow one, is the Kamioka mine. So this is where the Kagra interferometer will be. And you can see right away it's a huge benefit. There are not so much more wonderful below 1 hertz, but all of these sources of all of these human sources of seismic noise are basically gone once you go underground by a few hundred meters. And especially the high frequency influence is gone. And this, although this is not a challenge for the seismic isolation, it's important for the seismic sensors because they're not very linear. This is the quietest place in the United States that I've found. There's a project. There's a project called the U.S. Array where sets of seismometers are moved across the whole of the United States, and so there is a movie that you can see which is showing the time variation of seismic noise in all frequency bands with a grid spacing of something like a few hundred by 100 across the country. And you can look at these over time, over the course of a year or something. This one has almost no time variation. So there's very little day-night variation and also very little seasonal. And what's remarkable about it is it's very close to this dashed line. This dashed line is the Peterson new low noise model. And what it means is this guy Peterson took seismic data from all over the world, and in each frequency bin took the lowest point that could be found anywhere in the world, and then made of this composite trace. So this thick dashed line doesn't actually exist really anywhere on the Earth. But the minimum, or the idea is that there's no place on the Earth where you can get anything lower than this. So this, and there's also another one called NHNM, which you can guess what that means, and it's somewhere up here. So we all live in between these places, we think, although occasionally a really noisy place in the center of a city will beat the NHNM. Anyway, so these two are underground, and the remarkable thing about this blue trace is that it can be, you can do it on the surface. So to those who say we need to go underground, I say, phooey. Look at this, just go to Texas. And Texas is, Texas is not unique in the world, you just have to search. And you should be able to, if you try hard enough, and if you work hard enough and your seismic sensors are good enough, you too should be able to do as good as Texas. I should get a T-shirt that says that. So what can we do with sensors? This is from this really nice paper by Ringler and Hutt, 2010. They make a comparison of, oh, wait, I skipped a point. So what about these sources? This low frequency thing, this is a Earth-based thing. You can't do much about it. This is what we generally call the microseismic peak. It's really the secondary microseismic. The fundamental one is this one down here, and then the double frequency of this one produces noise in the band from around 0.15 to 0.35, depending upon the stormy conditions and where you are. You can see here in Virgo, it's sort of high. Some of these LIGO sites are low. It moves around. There's nothing you can do about it. Also, during the stormy time, wind also produces a lot of noise here. And that is extremely troubling because, as we'll see later, the wind pushes on the walls of the building, and the force on the wall produces tilt of the floor slab. And tilt is the enemy of all seismic isolation experts. It's the enemy, but it's also the prize of all seismic isolation experts. In this band, it's mainly due to things like people making noise and vehicles and maybe some machinery, but mainly just these things. And so you see a big variation in these, which just depends on the local population, mostly. Then once you get into this band, it has something to do with machines and vehicles, but also to do with the stiffness of the Earth. And if you are measuring in some hard-packed, rocky place, you will do good in the low frequencies, but you may easily have high frequency or high-level noise at high frequencies. And all of these sharp lines that you see here are due to local machinery. It's almost not due to any electromagnetic interference, but real machinery. The other point is that it has to do with what Peter mentioned about the Newtonian noise, and that I'm firmly on the, I don't know if it's left. I think I'm in the left wing. I believe in a progressive. I have a progressive viewpoint of Newtonian noise. I feel like as long as we, the community, have decided where we're going to focus our willpower, then it's a problem that's just a technical thing. We'll take care of it. So once we've decided that we need to go to 1 hertz on the Earth, we'll do it, and using the techniques that he was talking about. But it makes it much easier to do if the site that you've chosen is stiff, and that you can imagine the seismic waves moving coherently through there. It's not full of voids and full of mud. If you can model it as basically a solid block, then it's easy to see that the waves will be coherent quite a bit better, and simple models of wave propagation will allow you to estimate how many sensors you need in order to subtract off the noise. I don't know. It's in my list of maybe when I get back, I'll take a holiday to make up for this missing my Christmas holiday, and I would explore. I would take a drive down to this place. This is in the west. I don't know what to call it. It would be like Panhandle. It's like the west arm of Texas, near El Paso, close to New Mexico. Actually, the whole region between the Los Alamos slab and this Mexican border is a interestingly low noise area. There's some Native American reservations around there which stop the development of real big cities. And then, of course, Albuquerque, close to Albuquerque, there's some national labs, defense labs, and things like that. So the whole area is quite underdeveloped. But I don't know yet. It's a good question, and I mean to get to the bottom of it. If we have some time during the discussion time, I'll show you my sketch for a dream 4th generation LIGO site. So something about some sensors. Very often they plot it in these units, which is acceleration noise, PSD. So it's meters squared per seconds to the 4th, or meters per second squared, the whole quantity squared. And this is dBs relative to one of these. So it means minus 180 means an acceleration of 1 nanometer per second squared. Okay? So if we want to plot displacement noise on that, we have to tilt it by this. And so this is displacement noise. This is acceleration. There's another feature which comes. So you can see the X scale is very different here than what I showed you before. Before I cut it off below here because we just don't have any data down there. Because this is data taken mostly by people in the gravity wave business, and this is data taken by professional seismologists who know what they're doing with seismic stations. So they're able to actually measure the internal noise of seismometers to below a millihertz because they spend all of their lives learning how to do this. So there's an array of sensors which are good, and you can see compared to the low noise model, it's not so uncommon to be able to measure better than anywhere on the Earth from sort of tens of millihertz up to maybe tens of hertz, depending upon what you're using. In these plots that they make, they don't even plot. They put the legend to cover their data in this region because they don't consider it really seismology anymore. Once you're above 10 hertz, it's acoustics or something. And large, you'll never be able to measure anything down here because, as it turns out, almost all of these devices have a nonlinearity that down converts the high frequency acoustic shaking noise into the low frequency band. You can imagine if, what's a good analogy? Sometimes, yeah, there's these memory foam seats, and if you poke the memory foam seat really quick and take your hand away, for the next minute or so, the seat will slowly reform itself. And that's a form of acoustic down conversion. And seismometers are not made out of memory foam, but even the best even the best metals or glasses or things like that will have this sort of relaxation effect, which will allow for energy to be converted into the low frequency band. So this is a picture of one of the earliest good seismometers. This is from, yes? These two? Oh, they have different sensors. Yeah. Oh, maybe, yes. If you don't spend your life studying these things? Oh, you mean what is this one? Which one are you asking? Why did I do this? When earthquakes are distant, all that we see from the earthquake is the low frequency waves which travel through the Earth, and those happen in this frequency band. So if there's a nearby earthquake, as everyone knows, it sort of the impulsive thing happens and your bed shakes or something. But what we see usually is if there's an earthquake on the other side of the world, then you see large waves at tens of seconds period. And this you'll see just a peak like this, and then I think these T120 and T240 are from this Trillium company, so those are comparable. T240 is comparable to STS2. T120 has a 120-second period. I don't remember a T-compact. You have to be a true seismic aficionado to be memorizing all specs of all code names in your head. I know maybe 50%. Yeah, they have a vault and they put all of these sensors together and do all the cross. There's an interesting method for measuring self-noise. You can ask me later, but there's a technique for measuring the self-noise of seismometers, which is called the three-corner hat approach, which is the same thing that you use for doing 3-laser phase noise or 3-oscillator phase noise. It's a similar technique. It's what you can do if you don't have two of every seismometer sitting there. So let's see how this one is made. This is Streckhuysen is one of the top names in high-class seismology. He and Wieland wrote this paper in 1982, around the same time as Geralp wrote his famous paper on what became the Geralp seismometer. And those are widely used as broadband low noise systems. You can see what's going on here. There's a flexed metal hinge here, and there's a moving mass, and this so-called crossed hinge system. But this spring here, which is this spring, this is really it's sort of an analog of these springs that Peter was showing. They're thin and they're made so that they have minimal hysteresis and they have wide, just minimal hysteresis, I guess. There are a lot of practical considerations that go into this. You want low temperature drift and low thermal expansion of the spring, and so on. This is just some, I guess, some trivia about seismic sensors and what you would use. Almost the best thing that you can do for our band is to use these broadband systems, the STSs, Trilliums, etc. Things like STS2 and T240, they're really broadband. They measure noise lower than anything that we need over the whole band of interest for us. And they're somewhat portable. Things like STS1, you need a professional to come in and set it up for you. It's way beyond kind of amateur levels. But they're pretty good. They use force feedback so that the spring doesn't really move. There's a force actuator which keeps the spring from moving, which seems a little strange. If the spring is not moving, how do you measure your signal? Yeah, but of course it's the same reasoning of how gravity wave interferometer works. We have a huge bandwidth feedback. The whole over part of the gravity wave band, the signal is nulled, and we still are sensitive. It's the same thing for these guys. They use capacitive sensor to measure this moving mass and do a feedback. So we use interferometry to do mass measurement. Anyway. So they're moderately expensive, $20,000. So you really treat them with care. To go beyond this, you can get into the realm of truly ultra high class luxury seismometers, like these Lacroste-Romberg gravimeters, which have fused silica springs, and it's a real, almost research grade device. And the reason for doing those things is, if you're basically in a deep, deep mine and the noise is really low, or you're putting your sensor on the moon, or some extreme purpose like this. Of a slightly easier to use kind is these so-called geophones. There's no force feedback. The motion is read out by velocity. There's a coil magnet pair, so you can see the velocity. And they range over a whole wide frequency band and sensitivity level. You can get, the cheapest geophones are around $1,000 of this size. And they're pretty good, but not very good at low frequencies. And then there's the king of all geophones, this GS13, which allows you to get better sensitivity even than some of these sensors in the single axis. And then for high frequencies, for doing these things like measuring acoustics or getting subtraction of the gravitational noise, you can use something in between these low-priced geophones and even lower-priced accelerometers, which almost don't have even a moving mass, just a strain sensor. So this is where this is where they all come together. These are the sensors that we use in, I think, most of the gravity wave projects. This includes LIGO, Virgo, and Kagra. We're using more or less the same sensors at this point. And people are always trying to develop some better sensor, but more or less this is where it comes out. You can see the inertial sensors like STS, L4C, whatever, they're pretty good above a few tenths of a hertz. But at low frequencies, because they're velocity sensors or because there's some mass spring thing going on, they're not so good. And so you have to, there's some complication. If you want to do some sort of seismometer-based feedback to control your system to lower the noise, then you have to use multiple sensors and combine them in some kind of way, and it's going to be complicated. I want to now describe a little bit about how the seismometer works, and I'll leave this up here so you can read what are the limits. But now that we understand the linear system and this harmonic oscillator, we are perfectly poised to be able to design our own seismometer. And I think I've been thinking about this for a few years, and I feel like if we had some clever, hardworking people looking for some way to make a big impact in this field, then making a new, better seismometer would be one of those things. One not engineered for seismology, but just for this purpose of doing active vibration isolation. So let's use a. So this is a not even really a cartoon description. It's a real one. So let's say we have a fixed hinge here, and there's a spring, and then there's a moving mass which is magnetic. Okay, it's a little bit fake, but let's allow me that. And then we have a coil that reads it out. So there's M, some stiffness, and then how should we read it out? Let's say, yeah, let's say we just have some readout like this. What's to be done, or how do we read out this thing? So this thing is fixed to the ground, let's say. And so now the ground is moving. And when the ground moves, if the ground moves very, very slowly, like we just saw in Peter's transfer function, this mass will not move. It'll just, or it will move along with the ground. And so as far as velocity or motion between this mass and this coil, there won't be anything. And at some high frequencies, if this ground is really moving, then this thing, because it's only supported by this spring, won't be able to follow it, and you'll see some sort of motion. So there should be, qualitatively, before we calculate anything, there should be some low frequency cutoff below which we wouldn't use this kind of sensor. And above there, it's a good inertial sensor. Right? So let's use some, so we can start with our Newton's law, F equals mx. And what are the forces on here? Well, we have this spring, and we can also apply some, let's say there's some sort of damping to it. And we can give it this damping factor B. So then we can just write down the equations of motion for this. So here I'm just saying, what's going to be the acceleration of this mass? There's going to be two forces acting on it. One is this restoring force from the spring. Restoring force from the spring, and the other one will be the damping force, which resists velocity in this direction. And I put in these minus signs so that it all makes sense. Yeah. So now we can do also the same trick for doing the frequency domain analysis, and we can assume that x ground is going to be some sinusoidal signal at frequency omega, and let's say what we want to do is find the response of the system also at that frequency. So x will be x0. And now it's easy. At each point we can stick in our guess for these solutions and then find what the final answer is going to be. So let me just skip some of this algebra. So after sticking these in and taking the appropriate derivatives, we can collect terms and get the ratio of motion of this mass relative to the ground. So here I've substituted that omega 0, the resonant frequency, is equal to the usual mass spring resonant frequency. So this already has the character that I described. At low frequencies where omega goes to 0, then you just get 1, which makes sense that you move the ground and the mass follows it. And at some high frequencies, this term dominates over these ones, and so you can see that this motion falls off. This one doesn't track the ground motion anymore. So if we plot this, we can see what. Let's see this ratio. This is going to look something like there's going to be this resonance peak, and then it goes down like 1 over f squared to the 0. And then there's this curious 1 over f region out here. And so this is, I guess, the other downfall to passive passive seismic isolation. In this case, we're not trying to do isolation, but this will show up if we try to use damped systems like rubber in our stacks. That at the beginning, as I said, these things are equal. As the frequency increases like this, we get this resonance. And then at frequencies where this term is much smaller than this one, we do get this omega's 0 squared over omega squared, 1 over f squared isolation. But then at some frequency, eventually, this term overtakes this one, and then the asymptotic behavior will just be this term divided by this one. And so that gives us the 1 over f kind of behavior. So it means that even if you make this kind of isolation system, because it has some dissipation, no matter what kind of mechanical system you use will have some limit. You can't do better. You won't get, in addition to these internal modes, you can't do better than this for the seismic isolation. So
if velocity damping is a good model for your dispersion.
If velocity damping is. Yeah, and so, yes, it's a good segue. I think it's a good question of whether or not this is actually true. And in the, if this was a gravity wave detector, what we would have is a little thing here, and this would go to our vacuum pump. But this is not the case for the seismometers. And in fact, what's going on is people try different tricks. Some of them are pressurized or not, but there's few of them which are operated at vacuum. Most of them are operated at room temperature, or standard pressure, room atmospheric pressure. And at atmospheric pressure, if you really want to evade this external velocity damping limit, then what you need to do is really make this mass big. And for some micro sensors, they're certainly not in that regime, so they're gas damping limited. And around the level where they get to a kilogram level, they're no longer gas damping limited. But as it turns out, they're still velocity damping limited, and it's a curious. I guess it's a curious thing why that's the case, and you wouldn't think so. I think if you open up these things and you see how they're constructed, it's a pretty clean metallic spring system, and you would think that it should have a Q of some thousands, but in fact, they're very far from it. So I don't have the answer, but it seems to be the case. Yeah. So okay, this is true. This is the ratio of the internal mass divided by the ground. But in fact, what we measure with our magnet coil system is the difference between these two. So we can do some more algebra and write this down. What we really would like to find out is something like what's x0 minus x ground over x ground. So it's what will be the apparent relative motion in here divided by the ground motion. And you can do some more algebra and convince yourself of what it is. You'll get yeah, and then here I've just replaced what have I done? Just to put it into our language of loss and mechanical Q. So this one shows you what I was describing before. If you look at this, what's this differential motion over the ground motion, you'll get that the high frequency asymptotic behavior is 1, which is good. It means that you'll be able to see the motion at high frequencies, and then as you go down toward DC, the asymptotically this thing will be 1 over f squared. So there's this cutoff frequency below which these kinds of sensor are not very sensitive. And for these geophones I was describing before, they're almost all uniformly 1 hertz or so. They're still able to do some sensing because the magnet coil or capacitive sensor in there is still working, but generally they're just used at higher frequencies. They're not broadband. So Yeah, there's some analysis of the thermal noise in these systems, and I give some references here that you can look up. But it's still a should no. Um, yeah, I think there are several designs. So in the Streckheisen, what they have is a 3 identical springs which are oriented at 45 degrees to the vertical, and so you have a 3-axis orthogonal pair like this, and then those individual signals are taken and algebraically recombined with analog circuits to give you XYZ value. Some of the broadband ones internally really do have XYZ sensors, but the the concept, yeah, this is not accurate for what the current Streckheisens look like, but the concept is that if you make a vertical sensor, it looks different from the horizontal ones, as you can see. The horizontal one could be pendulum, for example, but vertical one can't be a pendulum. And so the idea in making 3 identical ones and doing recombination is to avoid this disparity between them. You get equal noise and all. And then, of course, this kind of sensor can be reconfigured to be horizontal or vertical. If you put some preloading, then it can be either way. Yeah. So anyway, if you look here, they go through some of the limits to the preamp circuits that they've designed, and they do some analysis of the thermal noise. They look at the effects of the Brownian noise from gas interacting with the mass, and then also with the Brownian noise of the mechanical flexures. And after, well, really predating this stuff, there was people worked on fused silica, fused quartz seismometers, because they would have very low mechanical noise, and there was a lot of, it really foreshadowed a lot of the work that went into the gravity wave detectors. There were quartz springs. People worked on flame polishing of the quartz fibers and blades, and people don't seem to do it much anymore. So all of the commercial sensors now, almost all commercial sensors are metal spring based. Yeah. Anyway, you can work it out for yourself a little bit, but I don't want to go too much into this thermal noise part because we've rearranged the order and we'll do thermal noise later. But what we do know how to do is this electronics noise. So we can, now that we know the dynamics of how the mechanical system responds, ignoring the thermal noise, we can think about how to design the sensor. And we can, and I think we can do better. I've had some discussions with seismometer companies, and it looks like there are, surprisingly, there's still research to be done and readout of seismometers. Because it's such an old field, you think it would be all done, but it's not all done. Things to do. As they tell me, there are all these sort of dirty effects. So they said, you armchair seismologist, because you're a physicist, you may think you can totally model the thing and come up with all the answers. But there's all these dirt effects to think about, and it's true. But this knowledge is this has been well explored, I think, and the seismometer design companies know what they're doing. But I'll just describe a few here. So there's pressure noise in the seismometer case. You may seal the seismometer case. The pressure is controlled internally, but then you have the effect that if the air pressure changes outside, you have an overall buoyancy. The seismometer itself goes up and down. If you allow the pressure to change within the can itself, then the mass itself can float. The magnetic field, ambient magnetic field, couples both to the seismometer electronics as well as directly to magnetic materials which are in the box. And then, as I said, there's hysteresis and mechanical down conversion. So why do I tell you all these things about the seismometer noise? Of course, one point is that we like to know what's happening in the ground, and we use it as a way to veto our data and say, well, there was a bump or something like that. But if we could, then what we would, for example, we would just have a single pendulum, and then on the top of that pendulum would be a super high-class seismometer. And then all we would have to do is apply some feedback system to zero out the signals that were read by this seismometer, and that would be the end. And we wouldn't need this, 10, 15 stage pendulum system or lots of rubbers and springs and all this other stuff. And so, and it's quite attractive because these things are fairly compact. These biggest seismometers are around this size. Yeah.
We see that the seismometer has a precision of just 10 power minus 14.
Right. These ones, yes.
Okay, so there are seismometers which are more sensitive than 10 power minus 22, so that you can use it for a feedback system.
No.
And for a feedback system, we need detection up to 10 power minus 22.
Almost. Yeah, that would be nice, but it's the same. If we had a seismometer that good, we would not build a gravity wave detector, right? Then I would just. I would walk around the world with my seismometer and put it down, and from my hotel room, I would just read out gravity waves.
So how do we use it as a feedback system?
Yes, excellent question. This is the question that we are wrestling with currently. Yeah, it's good. It's a good. I'll talk about it, but that's the right question. How do we use it? The sensor, 10 to the minus 13, 10 to the minus 14, and we would like to be better by a factor of 10 to the 7 or 10 to the 8. Why am I even talking about active isolation then? Yeah, it's a good question. Sometimes I don't know. I'm just talking. But I think, let's see, do we have, what's our time? My computer can't read time anymore. 20 minutes? Let's take 5 minutes, since you all have pencil and paper, and let's try to calculate something about this seismometer readout, because this is the right question, is can we do better for a seismic sensor? And I think it's instructive to go through this, just a few steps of algebra just to see where you would get. So just to remind you, here's what's going on. There's this, this is it. And you can choose the parameters as you want. If you think that you can make a mass spring system that has a resonant frequency of 1 hertz or 0.1 hertz, put whatever number into here that you want. And what kind of mass can you have? Well, the best people so far have chosen mass of around 1 kilogram. So if you have a good reason to think that you can have something different than 1 kilogram, then please do. And then for the Q factor, use whatever Q that you think you can get with the metal system, steel or copper. This could be in the neighborhood of 1,000, let's say. So okay, this is the dynamics, and this tells you how to go from ground motion into this relative motion of the system. And then what else do we need to know? We need to know how good is our sensor, and then how good is our readout electronics. So I said here that here's 2 options. One option is to use some existing sensor, displacement sensor. You can try that and imagine that you put it into here, and then you can calculate for yourself what kind of ground motion you can sense. Another way is to use this magnet coil readout that I described here, and then to use some circuit. You have all of the pieces now. You know how to calculate Johnson noise for circuits. You know how to use preamps. You know how to make op-amp circuits and calculate noise of op-amp circuits. So I think this should be less than 10 minutes kind of exercise. So what will the op-amp circuit look like? It's well, just what I've drawn there. You've got this moving magnet creates a electromotive force in the coil, and then the signal comes out. So you can say, I have this signal generator, I have some inductor, L, and then I have some resistance. And if you take some reasonable wire and make an inductor coil readout, which is the size of a orange, then this could be something like 5 to 10 henries, and this resistance could be something like 4,000 ohms. These are what I remember. And then, so this produces a voltage, and then you can do something like this. And this Z is some complex impedance that you're free to design. That's the circuit that you can add in here. And here, just to make things easier for you, I'm already suggesting what's a good op amp. There's this FET, best for seismology op amp, which has input noise of basically 0 for the current. It's like less than 0.1 picoamps. And voltage noise of, I don't know, I think it's less than 5 nanovolts. Is this enough information? Am I leaving out something? It might be.
How do we make sure whether the supports are really rigid?
Yeah, I can tell you, but then it would be 1 more hour. In the construction of the seismometer, they take some care so that the legs are stiff. But then there's a real problem right in this area with the contacting of the legs to the ground. And that's a hot topic of debate all the time. That some have legs which are sharp and they dig into the ground. Some have rounded glass feet. Some people don't like feet, and so that they epoxy the whole thing to the ground. Then they cover it in sand, and then they cover it in a box, and then foam, and then underground, on and on and on. But maybe the real answer is you just don't trust this thing above 10 hertz because it's going to have some mechanical resonance problem. Yeah, I think I left out the main thing, which is something like how many volts per meter per second. So the generator constant. Generator constant. We'll say 5,000 volts per meter per second. And as you work on it, you can. This is not the limits of what can be done. Of course, tomorrow we'll find out about what's the kind of fundamental thermodynamic limit of this kind of device, independent of what sort of sensor we're using, and that will be an interesting limit. And then, of course, the other point, and then because you're doing it analytically, or because tomorrow you'll see it analytically, you'll see how one can scale the parameters of the seismometer to evade some of the apparent thermodynamic limits. And then there's several kinds of sensing, which we only looked at 2 here. There's this voice coil based one, which is actually used in many sensors. And as I said, there's capacitive sensing. Those are 2. Those all have limits, as you'll see when you calculate this thing. At this level, it's sort of 10 to the minus 10 to 10 to the minus 15. So those are the 4 or 5 orders of magnitude. I think the best capacitive position sensors are not better than minus 15. I think that's true. But we know techniques for doing better position sensing. Right? All of this week we've been talking about this strange 4-kilometer position sensing device. And somehow we're not employing that technology in this thing. It might be, a very, very easy way to make improvements in something is to just combine two things that are sitting around that somebody else has invented. And you can be a genius. Combine two things. So anyway, there's in this electronic circuit, this voice coil readout. That's one kind of noise. If we decide to do interferometry, we'll be limited by some other kind of noise, probably just the shot noise of our interferometric sensor. And so then the challenge will be of how to fit a small interferometer into this device, but it can be done. And we'll see that there's the thermal noise. And if we can truly get big improvements of this, then this idea of using active seismic isolation starts to look more and more promising, I think. If it's really true that we can only do as like this, 10 to the minus 10, 11, 12, well, what good is that? Well, I think the point is it's not a all or nothing game. We can use, the best of each. So let me, just to move on, I'll just get into now some more of how the active isolation works in LIGO, and then we can, over the lunch or during the discussion period, we can go over what the circuit calculation came to. So this is a diagram of the LIGO system, and you don't have to pay attention to all of these things, but basically there are two kinds of seismic isolation platforms. There's these ones which have the yellow outline where the real gravity wave signal is coming in, so they're high-class ones, the isolation factor is good. And then there's these gray ones which are something like half the isolation capability of these ones, where these are a single platform active isolation system, and these yellow ones are double. So what do I mean when I say active isolation system? So again, because we don't want to get today too deep into the equations of feedback, I'll just draw the diagram. I'll just go through this diagram for you, and then we'll see what it really means a little bit later. So we start off. Here is this table where everything is sitting on. We have some sensors. These steel chambers are meant to keep the dirty seismometer from getting into our clean vacuum system. So these sensors are inside of this table, which is supporting our system. Then the signal goes through some filters, becomes digitized. Then we take it and we combine the different sensors, as I was saying. So we use each sensor in the frequency regime where it's optimum. We put them together, and then we apply. This is the magic. The magic of feedback goes on here. So just allow me the fact that there's some magic. And then that goes back out. Some force is applied to the table, and the table is kept quiet. So at the same place where the ground motion comes in, we put in a force which drives the table around and cancels the effect. And this whole thing is done such that the signal coming out of these sensors is kept to be 0. So that's the feedback idea. And this happens. There's a loop like this for every degree of freedom, and it keeps it stabilized. And this is this very nice diagram, and several other nice diagrams I'll show you are made by Jeff Kissel, who is our seismic and suspension diagramming expert, and also taking care of making all of these systems work. And this is a web link you can look up. It has this presentation, which is a nice walkthrough of how all of these systems work. So this is the picture that Peter showed you before, but with now these elements filled in. So this is the concrete floor. There's a steel blue pier. There's some stuff here, it looks like. And then this thing, I liked Peter's word. It was a goonie. What do you say? Goonie structure. That's what it is. And then on top of this is another isolation system, and then below that is, here's the optic. So for the LIGO system, each of these legs is a mini active isolation system, and then these tubes go in. This is one table of what I just showed you. Below that one is yet another layer. So you get really 3 layers. There's this external thing, and then inside 2 more things. So it's a triple active isolation system. Why triple? I mean, I already showed you this thing, that we don't have any sensors better than this thing. If we already have one of those sensors, why do we need to keep doing it? Why would we have 3 stages of the same stuff? Have we found a big mistake in the design of LIGO? It could be, yes, but someone must have an answer. Very silent. Okay. Unknown. Well, we have 3 stages for some reason. You can keep thinking about it, and then you can answer me later. Anyway, this is how it's done, and some isolation is done. And now the question is, why would we do this? And this is I've showed you this before, but this is how the Virgo system is done. And this is just a blow-up of this pod that Peter was showing you before. In addition to the fact that it's a normal pendulum system, there are all of these metal triangular springs, blade springs, leaf springs. And these give you the vertical compliance. So in addition to swinging, these blades go up and down and give you some softness in the vertical direction. So this is what makes the system have good isolation in all degrees of freedom. And of course, all of the problems that we've talked about so far occur in this system. The internal modes are there so that these blades are only isolating up to maybe 100 hertz or something. And then because there's some friction and damping in these systems, the isolation freezes out at some frequency because it's some external damping. And this is just a comparison now of what do we get if we put side by side the performance of all of these systems and see really on the same plot how do they all compare. The system that you just saw previously, the initial LIGO stack of copper springs with the single pendulum stage, gives you this gray, theoretically anyway, gives you this gray transfer function. So you get this isolation of several orders of magnitude by tens of hertz. The Geo system, which Peter also showed you, which has rubber stacks, and then it's quite different. It had less rubber stack, but then it had triple suspension instead of single suspension. That one gives you almost the same. And I didn't line these things up. They're just by chance. They happen to be like this. So those are one class. And then here, this pink curve is the initial and advanced Virgo curve. And you can see it's, yeah, really good and gives you a lot of isolation here. And the advanced LIGO system, which has this multiple active stage system, and then on top of that gives you quadruple passive isolation by this quadruple pendulum that he showed you. That gives you this blue curve, we estimate. And I say transfer function in quotes because transfer function is no longer appropriate to describe the performance of these systems. Transfer function is something that's useful for purely linear systems. So it means here's my system, I inject noise, and then I look to see how much noise shows up at the bottom. But we've already seen that this is not going to work because look at what's happening here. I have this going on. So ground motion comes in, it goes onto this table, and then what's happening here? Well, it's not that the motion goes through here linearly with no trouble. In addition to the signal for the ground motion, this noise is getting injected into that sensor. And so the transfer function implies that as I reduce the ground motion further and further and further, the motion of the platform will get better and better and better. But of course, if you're limited by the sensitivity of your active sensing, that's not true. So instead, what I'm showing you here is something like the ratio of the ground noise to the ratio of the noise on the inside. It's not strictly transfer function, but it's a ratio of the magnitude. So similar. Anyway, so there are a lot of traces here, and so the question remains: why would anybody make this choice? You look at this curve, this blue curve. Look at this pink curve. Pink is clearly less than blue here. There must be some logic. It's not that these LIGO people are all just crazy or like they can't produce these kinds of plots. I could produce this kind of plot in less than a day. So if you look at this, you may, I mean, qualitatively, maybe you can come up with some thoughts. What are the biggest differences between, say, this blue one and the pink one, or this other dark blue one? Yeah, exactly. So this, based on the slope, you would definitely pick one of these two. Yeah. Ah, it's about the same.
Gamma looks like had a 3 stages of isolation, as well as advanced LIGO. Does it have an active system?
Yeah, that's another point. All of these systems are both active and passive. That's the theology Peter referred to. All of the systems are chiefly passive, actually. Even the LIGO system gets almost all of its action from passive isolation, and then the active part does something else. And that's what I'm trying to get you to see here. Maybe it's just that the plot is not good. If you look at this blue one, here it is. It goes slightly above 1, and then it's kind of smooth. There's some ripples and things, and it just sort of cruises on. But there's no peaks. Really. It just kind of goes. And then you look at the red one, the Tama one that you described. The Tama one, this is an upgraded Tama So the red one, Kagura, Virgo, they're all of the same type, which is this cascaded multi-pendulum. And what you see in all of them is that they have these super sharp resonances all over the place. And to defeat those, they've added in some active damping to damp those systems. But what's the problem with having something like this in your system, whether you have high Q, low Q amplification? I mean, we're detecting gravity waves here. And why am I even talking about any of this stuff? Who cares what's the difference? There's a few orders of magnitude at 1 hertz. Yeah, it's a subtle issue. And it has to do with the fact that I feel like I'm attacking Peter's lecture, but I'm not. Linear systems are really important, and it's especially important to realize when the system becomes not linear. And the real reason this design choice was made was to handle the nonlinearity in the system. And if the system is linear, of course, you can make, you're free to make the Q of these things anything you want, and then the system will move around by microns, or if you have a Q of 100, by 100 microns at low frequency, and you can do whatever detection you want at high frequencies. But of course, that's not the case. There's several levels at which the system becomes nonlinear. There's the Michelson fringe issue that Peter described. So the Michelson fringe, something like this, you might look at this thing and say, well, this has a linear region of something like that. And if this is one wave, then it could be this is something like lambda by 5. Maybe that's true, right? Well, then we talked about the Fabry-Perot cavity resonance. If we have a Fabry-Perot cavity that has a buildup factor of 100 or something, then maybe this has a linear regime, which is something like lambda over 100. Okay, so now we're getting into this sort of 10 nanometer regime. 10 nanometers doesn't seem so bad. at some of these quiet sites, maybe we could get away with it. We wouldn't need any worries about this low frequency business. But 10 nanometers is really still not the real limit to the linearity. And it has to do more with the fact that this Pound-Reaver-Hall scheme we were telling you about yesterday is also highly not linear. That's if you did, or if you're still going through the calculation, if you continue to work it out, what you see that as you get from resonance in this near this line width, what the signal looks like is something like this. So right here at the zero crossing, it is in fact very, very linear. So okay, but if you did some sort of Taylor expansion of this system, you'd see that the first thing that you'd have to do is add some sort of curvature term, because the slope changes here and it turns around. And so the question is, for what kind of distance is this approximation correct, that the system has a linear readout? Yeah, I don't know. You have to work through this and see what it is. But the way to do it is to say, my signal readout V as a function of x, let's say, is going to be something alpha x, and then it's going to have some new term, like it's going to have something like beta x cubed. And the question is, at what level is this next higher order term becoming important? Well, it becomes important at the level at which your gravitational wave sensitivity is compromised. And the you know, if you look at these things and look at how many orders of we have on the y-axis, it's clear that we're working in a regime where we will be extremely sensitive to even the tiniest beta term. What we're saying, what we're saying is a remarkable thing. If you look at the strain sensitivity curve, what we're saying is something like, here at 1 hertz, we'll have motion of 10 to the minus 6, and somehow here at 10 hertz, we want a motion of 10 to the minus 19 meters. You know, can you imagine something that goes by 13 orders of magnitude in 1 decade? It would never work. It means that, you know, if you take this and you put in, you say, I'm moving sinusoidally at 1 hertz at 10 to the minus 6, you can ask yourself, what would the ratio have to be of beta to alpha, so that I wouldn't, instead of getting just a sine wave here, I would get also sine waves here and here and here, and would ruin my sensitivity. So you can work it out for yourself, but the answer is that beta has to be much smaller than alpha. And this is not a degree of freedom that we have. This is just the shape of the readout. And this is just one source of nonlinearity. It's maybe the first you can imagine. Of course, there's more having to do with mechanical systems and electronics of actuators or something. But it's very difficult to try to ask for something like 13 orders of magnitude of linearity in a system. And so because of this, it's very important for us to control this low frequency motion. And we don't want to have multiple microns of motion here. In fact, we would like to have orders of magnitude of seismic isolation already at 1 hertz. And so that's the main difference. That it's sort of just like what you would expect if you were designing analog filters, that if you made a high Q Chebyshev filter, then you can get a lot of attenuation close in. And if you made some low Q system that didn't have a lot of amplification here, like Butterworth filter, you would have a softer slope, but you would get less amplification in the passband. It's like, there's no way around it. There's good causality arguments that tell you what you can and can't have. And as Peter says, everything fails at low frequency, but there's failure and then there's failure, you know. So there's some failure where you're just unhappy, and then there's other failure where you're, you know, the U.S. Congress, you know, ridicules you, and we don't want that kind of failure. Let me just skip this. I just want to say there is a problem, tilt horizontal problem. You can read about it. Many people have worked on it. I put their names here. But the issue is just that when the ground tilts, the seismometer sees it, and it's a difficulty in. Yeah.
4 actually.
Okay, if you count that very low one.
You have to count them all.
Yeah, so if I start, if I take the blue one, not the blue, but pale blue, what we call it, is 1, 2, 3, 4, 5, 6, 7. I mean, isn't that the reason why the slopes are different?
That's asymptotically why the slopes are different. But this close-in attenuation difference has to just do with the Q of the piece.
So,
At something like 10 hertz or 50 hertz, it's just the order of the number of stages in the sine system.
So why is the Einstein telescope preferring something like Virgo? They would have the same issues that you have about in terms of.
Yeah. Well, it's a design. It could still be debated. This thing I'm talking about, nonlinearity, we don't have a real, like a unified nonlinearity theory or something. It's all this people like me saying, well, I don't really like this. I think it's going to be a problem. It would be better if we had some quantitative way to evaluate it. Sort of say, well, we can have this, but we need to have this much suppression at 1 hertz and 0.1 hertz.
But in principle, one could just
make a very elaborate finite element model, 10 stages, and steep or something, and it will show you at least some problems.
Yeah, I think so.
That nobody is doing this. And that's what it is. I mean, for example, Einstein telescope, I can see, since it is meant to be underground, there is a lot of space for stacks after stacks, long pendulums. So it makes sense at some level, unlike a laboratory.
Yeah.
You can imagine
Yeah.
25 meters of isolation.
Yeah, well, some of us are doing experiments to try to find this nonlinearity in mechanical systems, and the nonlinearity in the optical systems we know about. But I think the model hasn't been done, so that's work that needs to happen. The real answer is that these seismic sensors are good at low frequencies. They're better than what you would get. It's very difficult to make a 0.01 hertz pendulum like that, but it's not so hard to just use the sensitivity of the seismometer at something like 1 hertz. But it's no good at high frequency. So the real answer is we just need to think carefully and do the right combination of active and passive systems to get the best thing. Of course, you have to use both. There's no sense in trying to put together. I'll just say a few words about this idea of. I think it often comes to mind when we're talking about this isolation systems. We say, why not just do magnetic levitation? That seems great, right? We can use superconductors and superconducting spheres and helium or electrostatics, or if we were really cool, we could just use super high power laser beams from below and use the laser beams with radiation pressure and levitate everything. And probably, but all of these things are really hard, and it doesn't solve the problems for you. This is what we're doing at Caltech is a magnetic levitation system. There are 6 magnets holding up a plate. This thing actually levitates, but we don't have any measurements of the noise. Anyway, it can levitate. This is a proposal by Giotto, one of the leaders of the Virgo collaboration, to use electrostatic levitation. And the idea just there is, you can get 2 plates together and you get some pulling force or pushing force, depending upon how you charge it. And this is his drawing of a way you can put lifting plates all over this thing, make a composite mass, and put a high quality optical thing here and levitate it. And the idea is basically, because you're not touching the mirror anymore, maybe you don't have any thermal noise problems, and because you're able to tune this thing, you can make the resonant frequency be tuned to arbitrarily low frequencies. And that sounds pretty cool, I think. But it's a mirage in the desert, I think. There are problems to all of these schemes. I say this even though I am personally pursuing magnetic levitation. Yeah, you can eliminate the suspension, but you find that all of these magnets have some conductivity, And when people in the past have tried to do superconducting levitation, they find that the field is expelled in the superconductor, but then there's losses in the surrounding vacuum chambers or something like that. Eddy current losses are always limiting what they can get. Then the stability is limited by the Earnshaw's theorem. I'm way over time? Ah, okay. So I just leave this here. You can read these points. But it's hard.
What is DOI? Degree of freedom.
Yeah, okay, anyway, that's my conclusion.
Okay, I think we can take questions over lunch. Come back at 2.